Assalamu alaikum. Can you hear me? Can you guys hear me properly? Okay, so let's start with the class of today. So we'll be covering the topic of stationary waves because we did uh, superposition and the general wave properties that chapter we've done. So we'll be proceeding with this. But before I do, I'll just recap a little bit of theory. So the stationary waves are basically waves which are superimposed in such a way that the effect of them, obviously we know that when waves like interfere with each other, their amplitudes add up, or by the resultant amplitude of the wave is the algebraic sum of their individual amplitudes. So that's something which we know. In Yeah, so the idea is the same, that when a wave is traveling forward and it hits a barrier and it reflects from that. So what now happens is they're like two waves which have been superimposed on each other, and they sometimes interfere in such a way that we end up with what we call a stationary wave. And the idea behind a stationary wave is that the wave does not move any forward, or just the idea is that this wave does not transfer any energy. And what we can say about these waves is the resultant wave could be given by these red lines, or which I've shown on this side. So it's either this way you could do this, or it's either how you like, or you can look at this graph as well. So either of the ways would be fine. So the idea is that at one instant, time t equals 0, the wave would be something like this. The wave would be like this. And then at another instant, which is after a quarter time period, just a second. After a quarter time period, there would be no wave because the wave is just gone. It's gone down. And then after another quarter time period, which is after half the time period, we have a wave which is exactly the reversed as the wave was before or initially. And then again the same pattern until we get time t equals t, where one whole time period has been completed. So this is just some diagram of a stationary wave, and this is some of the labeling which is important. So there are 2 points which are of considerable importance on a stationary wave. One is the antinode and the other one is a node. So the nodes are points on the wave. Obviously we know that on a wave it are the particles that oscillate. So nodes are those points on a wave where the oscillation of the particle is zero. The particles do not move. And antinodes are points on the wave where they have the maximum amplitude or the maximum displacement. So those are points, those are antinodes on the wave, and the other points are nodes. So, and then obviously we know the separation between these points, or before separation, if I just talk about this thing, that if this is my antinode, the particle would be oscillating up and down in this motion throughout time. And the point on the node would just remain stationary. It would have no sort of motion whatsoever. So this is just a simple antinode and a node. And then we come to the separation, or the distance between two adjacent antinodes and two adjacent nodes. So the distance between two adjacent nodes or antinodes is half wavelength. So they're not one wavelength apart, which is a very important point. If you see a stationary wave, don't assume that it's just like a progressive wave, that you just say that one point. Obviously it's very likely that we could confuse this antinode as a crest and this another antinode as a crest as well. So it's likely that someone might say that since this is a crest and this is a crest, this would obviously be one wavelength. No, this won't be a wavelength. This won't be a single wavelength because these are antinodes and not crest. So this is something which could confuse some students. So just keep this in mind. And then the other distance is separation between two adjacent no, node and antinode, like an antinode and the next antinode, a node, and the next antinode that comes after it. What would be the distance between these? So that's quarter wavelength. So this is all like some brief. theory. So now we'll come to some questions, and today's class will obviously be a little bit like short because obviously we have exam tomorrow. So we'll just keep it short and some important questions I thought you all should do before the exam. Okay, so state the condition required for the formation of stationary waves. Okay, so I'll come to this part later on because there's this another question of 3 or 4 marks where I'll like give you the key points which are necessary if a question like this comes. So we'll do this when we come to that part. Okay, so now we can read the statement. One end of a string is attached to a vibrator. The string is stretched by passing the other end over a pulley and attaching a load as illustrated in figure 4.1. The frequency of vibration of the vibrator is adjusted to 250 Hz and a transverse wave travels along the string with a speed of 12 meter per second. So the speed of the wave is 12 meter per second and it has a frequency of 250 Hz. The wave is reflected at the pulley and a stationary wave forms on the string. And this is the important part, like this will enable us to solve this whole thing. Now figure 4.2 shows the string between points A and B at time t equals t1. And now at time t equals t1, the string has maximum displacement. Calculate the distance A and B, like the distance between A, B. So how do we do this? So the very simple way to do this is first we know what are the information we know. We do know the frequency of the wave, which is 250 Hertz. And with the frequency, we also know the speed of the wave, which is 12 meter per second. And now these two things are known. We know, so we apply the formula wavelength equals speed over frequency, and from this I'll get 12 over 250, and this will give me an answer of 12 divided by 250. This will give me an answer of 0.048 meters. So this would be the wavelength of the wave. This is lambda. Now we need to find what's the distance between point A and point B in terms of wavelengths. So I just told you guys that the distance between what point would be this? If this is my wave, point A, and this is point B, what is point A? What's the special term for the wave at point A? Anyone? We just said this. Can anyone tell me? Yes, it would be a node. So we have a node at point A and then another node at point B. And what's the distance between one node and the other node? So we just did this that A and the next adjacent node, which is let me call this point 2. So A and 2, what's this? This is half the wavelength. So I know this, it's half the wavelength. And obviously a point here till a point here would be till the next adjacent node would be another half wavelength. And then obviously this would be another half wavelength, lambda over 2. So I know this. So if I add all these distances up, so this would come out to be as 1.5 lambda equals distance AB. Now what's lambda? I just substitute the value of lambda, which I just found out here, and I'll just plug it in. So 0.048, and I'll get the value of lambda. I'll get the distance between point A and point B, which will come out to be 0.072 meters. So this would just simply be my answer. And obviously for this, we do need to know the distance between nodes and antinodes and all the stuff I just told you guys. On figure 4.2, sketch the position of the string between A and B at times t1 plus 2 milliseconds and time t1 plus 5 milliseconds. So for these type of questions, the first thing that you need to do is find the time period t. And obviously we know that time period t is 1 divided by frequency. And since the frequency is 250 Hertz, so I just divide this and I'll get my time period, which is 1 divided by 250. I'll get my time period, which comes out as 4 milliseconds. Okay, so now if I talk about the wave, what's the original position of the wave? This is how my wave AB is at time t equals t1, right? So this is how the time is. Sorry, let me write the notation correctly. Time t equals t1. This is how the wave is. This a time of 2 milliseconds. What's it equal to in terms of time period? Can anyone tell me? What is it equal to in terms of time period? 2 seconds. 4 milliseconds is my total time period. So obviously 2 milliseconds would be half the time period, right? So that would be t divided by 2. So the proper equation for this part could be t1 plus time period divided by 2. And for the next part, or this second part, 5 seconds, 5 milliseconds. Now 5 milliseconds is equal to what? T1 plus 4 milliseconds is equal to 1 wavelength. So obviously 5 milliseconds would be equal to 1.25 time period. So that's what 5 seconds, 5 milliseconds would be equal to. So this is how I actually phrase them correctly. Now, how do we solve this? How do we draw the position of this thing at these times? For this, you need to refer to this graph, which I just showed you guys in the beginning. This. So at time t equals like when the time period is when a time period of when a quarter time period has passed, the wave would become from this to this. So this is how my wave would change, right? So this is how my wave changes. And right now, if I talk about this part, it's t equals t1 plus half time period. So they're asking me at time t1, this is the wave I have, which is AB as shown to me. And what would be the wave after a half time period has passed? So after half time period, simply this wave will switch on and become this wave. So obviously I could just simply tell, and I'm drawing it on this diagram for clarity. So after half time period, my diagram would become something like this. So pink is T1 and red is T1 plus T divided by 2. So that's how the wave would be at half time period. And now the next part is after 1.25 time periods have passed. So obviously, if this is how the wave goes in a time period and this cycle keeps on repeating, so I could alternatively write it as this would be the wave at time t. This would be the wave at time t equals 1.5. Sorry, just a second. So if this is how the wave is, I could simply say that this is also the case when time t equals t. This is also the case when time t equals uh, 1.25t, and this is again the time period when 1.5t, and again 1.75t, and then t equals 2.0 time t. So obviously this cycle would keep on repeating, and then I could say this is equal to time 2t. So obviously this would keep on repeating. So I can just simply look at the wave and tell that if it's 1.25t, so obviously the wave would go from this point. If this is how the wave is at time t equals 1, this would become a wave like this. That's how the wave would move in a quarter time period. So obviously I can simply tell that if we're talking about time t equals 1.5t, this is how my wave would become. So is this part clear to everyone? Or if not, if anyone has any questions, feel free to ask. I if someone is having confusion, I'll try to explain it in some easier way as well. T equals t1 plus 1.25t. So I hope this part is clear to everyone if no one is telling me they have a confusion. Obviously, there's another way, like you could memorize how the wave works, how the wave actually varies in its time period. So if you know this, you can simply just by telling you how much time period has passed, you can simply tell how the wave would be at whatever time they've given you. Okay, so the next part, state the difference between a stationary wave and a progressive wave in terms of the energy transferred along the wave. So how's there a difference between a progressive wave and a stationary wave in terms of energy transferred along the wave? So the answer to that would be that energy transferred along the wave, uh, there is some energy which gets transferred along the wave in a progressive wave. But as I just told you guys previously, that because a stationary wave is formed by two waves superimposing at each other, and obviously they're sometimes interfering constructively and at other times interference destructively. So obviously when these constructive interference and destructive interference occur, there is no energy transfer because the wave is simply cancelling out with itself. So when it comes to progressive waves, energy is transferred along the wave. Yes, there is some energy transferred, but when it comes to stationary waves, there is no energy transferred. So just keep this in mind. The next part is the phase of two adjacent vibrating particles. So the thing is that when it comes to stationary waves, or when it comes to progressive waves, so two adjacent vibrating particles, meaning that if this was my stationary wave, progressive wave for now, and this is a particle. If pink is my particle A, then the adjacent particle to this would be particle red. So how are particle A and particle B different with each other? What's the phase difference between these two? So when it comes to progressive waves, all the points on a single wave, on a single wavelength, are out of phase. So that's what you tell them. But when it comes to stationary waves, the concept of phase difference is not valid in stationary waves. So we can, it's as if we can say that all points on a stationary wave are in phase with each other. So that's the difference. Like on in a stationary wave, all particles, not just two adjacent particles, rather all particles on the wave are in phase with each other. Whereas when we talk about progressive waves, any two adjacent particles are out of phase with each other. So that would be a difference. Okay, and the next part, a tube is open at both ends. A loudspeaker emitting sound at a single frequency is placed near one end of the tube as shown in figure 3.1. Said what is meant by an antinode of the stationary wave. So obviously I just told you guys the point where the vibration of where the point where the particle experiences the maximum vibration, that's an antinode on the wave. Okay, so now they've given us some data that the speed is this, the length of the tube is 0.6 meters. Stationary wave is formed with an antinode at A at each end of the tube and two antinodes inside the tube. So there are antinodes at the end of the tube, meaning there's an antinode here and there's an antinode here, and obviously there are two antinodes inside the wave, inside the tube, and obviously, so now to like before we can even proceed to solve this, you'll need to draw the diagram of how the wave is formed between this. So if point A, say A is our antinode, so this would be how a wave would be between any two antinodes. So this is how the wave is there. And now similarly, I repeat the pattern. So the wave becomes something like this. So this is simply how my wave becomes inside this tube, how the wave is being formed. Now state the distance between a node and an adjacent antinode. So I know that the distance between a node and an adjacent antinode would be this. Right? This would be my distance d. And I also know similarly what's the total length of this tube. So the total length of this tube is 0.6 meters. And how many such points? How many such points would there be inside the tube? Like how many nodes and like how many of these distances would be there? So if I do some rough calculation, so this would be another d, and then this would be another d, this would be another d, this would be another d, and then this would be another d. So I have 6 d's. So I'll write the equation. 6d equals 0.6 meters and d equals 0.1 meters. So 0.1 meter would be my answer for this. So I hope this part is clear to everyone. D would be equal to 0.1 meters. Now the next part, determine for the sound in the tube the wavelength. And this part is like super easy because I just told you guys previously, if you look at this diagram, the distance between any two, a node and an adjacent antinode is quarter the wavelength. So obviously this 0.1 which I just found was this 0.1 which I just found was quarter my wavelength. Just a second. What happened to the screen? So yeah, this node and adjacent antinode, that's equal to quarter the wavelength. So this is something which I now know. So I can just simply write the equation. Wavelength, quarter wavelength equals 0.1 and wavelength equals 0.4 meters. So this is just simply how I get my wavelength. And then they've given me the speed, which is 340. And then they've given me the wavelength, which I just found out right now. It's 0.4 meters. So obviously with this, I can find the frequency as well. V equals F lambda. From this, I can make F the subject and find the frequency. And now the next part is determine the minimum frequency of the sound from the loudspeaker that produces a stationary wave in the tube. The minimum frequency of the sound. Now, a way to solve this could be that you've either memorized that whole chart of harmonic frequencies. So that's a way, or there's another way. Like it's a bit, it would like you'll have to do some working, but you won't need to memorize some stuff. Okay, so before I get to that part, I hope this part is clear to everyone because the next part is dependent on a good understanding of this. If anyone has any questions, do ask right now, or else we'll move to the next part. Okay, so I guess it's clear to everyone. So then I'll erase this whole part because the next part is a bit different. And in the next part, what they're asking me is that what's the minimum frequency of the sound from the loudspeaker that produces the stationary wave in the tube? Now, obviously, a minimum frequency would mean the maximum wavelength. So what's the maximum wavelength of a stationary wave that could be inside this tube? And now, obviously, this information, this antinode and this information, it becomes irrelevant because they've changed the whole scenario. But what remains the same as is this point, the points on the end. If it's an open tube, could there be nodes on the open ends? No, they cannot be nodes on the open ends because nodes are points where there is no movement of the particle. But if I look at the particles on these ends, they can easily move. So there would always be antinodes on these open ends. This is something that I know already. Like I know from the theory which I've studied, the theory related to harmonic motion and stuff. Sorry, not harmonic motion, uh, harmonic frequencies. So this is something I know. So the smallest wave could be an antinode on this loudspeaker end and another antinode on the open end. So this could be my longest wavelength inside this. Because there is like it's necessary that there be antinodes on the open end and on the loudspeaker end because they're open at the tube, like the particles can move, so they cannot be nodes at these points. So there should be always antinodes at these open ends, and if there are antinodes on these open ends, this is the longest wavelength there could be. So this is just something we know. And obviously, so is this part clear to everyone how I made this wave, how I got to this wave of the longest wavelength? Is it clear to everyone? Do let me know, at least someone, so that I know that you're understanding. Okay. So now this is the longest wavelength there could be, and this distance. So this distance is essentially the distance between two adjacent antinodes. And we just, if you look at the diagram which I had shown you before, so it's wavelength divided by two, it's half the wavelength. And the half the wavelength is equal to 0.60 meters. I just make my equation that wavelength divided by 2 equals 0.60, and from this I get 1.2 meters equals my wavelength. So this would be my longest wavelength, and I know the speed and I also know the wavelength. So speed over wavelength would be equal to my frequency, and from this I could find the minimum frequency that there could be. And why is this the minimum frequency? Because we've calculated it for the maximum wavelength there could be for a stationary wave in this arrangement. There could be waves of longer wavelengths, there could be, but any wave longer than this, any wavelength longer than this won't produce a stationary wave in this arrangement. So I hope this part is clear to everyone. So if it is, I'll proceed to the next part. Okay, so the next question is state two differences between a progressive wave and a stationary wave. So these two differences are exactly the same differences which they've asked me above. So the thing is that when it comes to stationary waves, they don't transfer any energy. There is no energy transferred along the direction of the wave. Whereas in progressive wave, there is some energy transferred. And the next point is that on a stationary wave, on a progressive wave, all points within one wavelength are out of phase with each other. Whereas on a stationary wave, this concept is not even valid, or we can say that all points are in phase in a wave, in a wave. Yeah. So the next part is describe how stationary waves are formed between R and S. So they've told me that there's a stationary wave between a formed being formed between R and S, and they're asking me how the wave is formed. It is 3 mark question, and these 3 points, if you could write it somewhere or like have it with you, these would suffice if such a question comes. So a wave is formed from the source and is reflected from the metal reflector, which is my essentially plate R, and the reflected wave gets superimposed with the initial wave. So there was this wave which was traveling from point S and it struck point R. So when it struck point R, it got reflected. It got reflected in such a direction. So when these waves superimpose with each other, they superimpose in such a way that a stationary wave was formed. Why? Because they have the same speed, wavelength, and frequency. All these things. Either of these could be sufficient, or all three of these could be sufficient. So this is how a stationary wave essentially forms. And this is like, if you write this, you'll get the marks. And this is also somewhat the answer to this as well. State the conditions required for the formation of stationary waves. So the condition required could be that the waves should have the same speed, frequency, and wavelength, and obviously, yeah. So and like they should overlap. So the waves which are traveling, they should overlap and like superimpose on each other. That would be one condition, and the next would be that they should have the same wavelength and frequency. Like they obviously should have the same speed, but obviously when it comes to electromagnetic waves, all electromagnetic waves have the same speed. So that's not something unique to these stationary waves. So what's unique to these stationary waves is the wavelength and the frequency is also the same. Either of the terms, frequency or wavelength, being the same means the other one would obviously be the same. So that's how we write this. Now the next part is a microwave detector D is placed between R and S. Explain how D is used to show that stationary waves are formed between point R and S. So now the thing is that there are two features which I just told you guys on a stationary wave, which are the nodes and antinodes. These are like some points like unique to stationary waves. A node is a point where there is no movement of the particle. And obviously, if this is a sound wave and I bring a microwave detector, obviously these are microwaves, and I bring a detector at a node, so there would be no displacement, there would be no detection. Like the detector will give me a reading of zero because there would be no wave. The electromagnetic spectrum, there is no oscillation there. There is no disturbance in the spectrum. So it would give me a reading of zero. And then when I bring it to a region of antinode, so that would be a region of maximum amplitude. So there would be two special type of points when I am moving the microwave detector. There would be 2 points where obviously at one point the reading would be zero, totally zero, and at another point the reading would be a very high value, a very maximum value. So that would be a node and antinode, and from that I could conclude that there's a stationary wave which was formed between R and S. Obviously, you need to write about both of them, the node and the antinode as well. Don't just suffice with the node. Don't just say that there would be nodes or where there would be no detection. Like, because it's also possible that there is no detection because there is no wave at all. But the thing, or if you could say that there's a maximum amplitude region, writing just this point alone would not be sufficient because there's also a chance that there was a progressive wave or twice the amplitude or of a very high amplitude. So the thing is that differentiates this between so the thing which differentiates between these two are being a progressive wave or there being a no wave waves. There are nodes where there is no disturbance, and then there are regions of antinodes where there are maximum disturbances. So just a minute. For some reason, my screen stopped working, so I'll just share it again. By the way, if anyone has any questions regarding what we've done up till now, like feel free to ask these things, because if you're not getting it, there's no point of me explaining it. So just make sure that you're understanding what I'm telling. And is the screen now visible to everyone? Yes, I think it is. So I think there is no screen being shared at the moment. Just a minute. So now I guess the screen might be again visible to everyone. Yes, it is. Okay, so we were on part 3. I don't know what's happening now. For some reason, I can't find it. Just a minute. Okay. Yeah. Also, okay. So how the wavelength of the microwave may be determined using the apparatus in figure 6.1. How can we use this apparatus to determine the uh, wavelength of the microwave? So obviously, I just told you guys that there would be regions of where there would be no displacement, no detection, which are nodes, and then there would be regions where there would be maximum amplitude, which would be regions of the regions which are known as antinodes. So what we do is we keep moving the microwave detector, and any two consecutive points where there is no detection, like where there was I was at a node, and then I kept moving my microwave forward. There came a point where there was a node, antinode, and there was maximum displacement, but I ignored that and I kept moving my microwave forward till I went to the closest point where there was again no displacement or no detection on my detector. So from this, I know that these 2 points were nodes where I was initially and where I am now. So I would find this distance, measure this distance between the previous point and the next point. This would be equal to half the wavelength. And then from this, I could calculate the whole wavelength. So that's how we do this. And now the wavelength of the microwaves is this. Calculate the frequency in gigahertz of the microwave. So obviously we do know the speed of microwaves. They are electromagnetic waves. So the speed would be 3 times 10 to the power of 8, and we know the speed, we know the wavelength. So from that we'll find the frequency of these microwaves. So that's how just you do this. Okay, so now the next part, define the wavelength of a progressive wave. So obviously, what's the wavelength of a progressive wave? Anyone, how do we define this? Or yeah, so previously till O levels the questions were different. They wouldn't ask you about wavelength or like what, but when it comes to AS level they would ask you what a wavelength is or how do you define a wavelength. So what's a wavelength? So basically wavelength is the distance moved or by the wave, the distance moved by the wave during one oscillation of yeah, during one cycle. The the distance moved by the wave during one cycle or one oscillation or one time period. So that would be wave. And what is meant by an antinode of a stationary wave? So an antinode would be point where the amplitude is maximum of the particle of the wave. Okay, so now the next part, and this part is a bit important, and this part is a bit could be like somewhat confusing and a difficult sort of question. So like just pay attention to this a little bit. Okay, so the question is, a loudspeaker producing sound of constant frequency is placed near the open end of a pipe. So if it's the open end of the pipe, I know for sure that there will be an antinode over here. This is something I know for sure because it's an open end an open end and an open end, and at open ends the particles can oscillate, so there would definitely be an antinode. And I also know that this is a piston, so a particle which is like just beside the piston, it cannot move. There is some concepts involved, like this concept of viscosity and stuff, which like it's beyond A levels. So that there are some reasons why particles, whenever they are across the surface, we call this boundary region in thermodynamics and stuff. So the particles which are just on the boundary of a surface, they cannot move. They don't move. So the particle on this piston would not move. So I know for sure that a particle here would be a node. So this is surely a node, and this is surely an antinode. So this is something I know. And whenever such a question comes, like identify the points where there will always be nodes and antinodes. This is important. In the previous question, when there was this question, so I knew for sure that there would be antinodes on the ends of the tube because they're both open. And if both ends are closed, like in this one, or like in this case, so both these ends were closed, so this end is closed and also point B, so obviously there would always be nodes at these points. This is something important, keep this in mind. Okay, so now a movable piston is at a distance x from the open end of the pipe. Distance x is increased from x equals 0 by moving the piston to the left with a constant speed of 0.75 centimeters per second. So that's the speed which with the piston is moving outwards. The speed of the sound in the pipe they've given me, and they're telling me a much louder sound is first heard when x equals 5 centimeters, 4.5 centimeters. Assume there's an antinode of a stationary wave at the open end of the pipe. Determine the frequency of the sound in the pipe. And obviously, these assumptions would always be what I just told you, based on what I told you, that there would always be antinodes on open ends and nodes on closed ends. So, like, just remember this. So, now a much louder sound is first heard when x equals 4.5 centimeters, meaning a much louder sound is first heard, meaning that there is an antinode which has just formed on point A. Obviously, if when the stationary wave would only form when the piston is at a distance x. If the distance of this piston was any what less than x, if it was any less a distance x apart from the speaker, there wouldn't have been a stationary wave. So the idea with stationary waves is that it only forms at specific regions or specific distances. So there wouldn't have been a stationary wave if the distance was any less than x. So before point x, they were just a progressive wave which was being reflected by the piston and stuff was happening. It was superimposing in different ways. So now what happens is okay. So a much louder sound is first heard. So obviously this tells me that the first node, or meaning the wave of a first harmonic frequency is just formed there. So assume determine the frequency of the sound in the pipe. So obviously if this is the case, how would I draw my wave? My wave would be something like this: node and antinode. And obviously I know x equals 4.5, and this thing is equal to wavelength divided by 4. So wavelength divided by 4 equals 4.5, and from this I could find my actual wavelength, which would be equal to 18 centimeter or 0.18 meters. And if I know the speed, I could simply say that my wavelength, sorry, no, not wavelength, my frequency would be equal to speed over wavelength. So speed is 340 divided by 0.18. So my frequency would come out as 340 divided by 0.18. So my frequency comes out to be approximately 1890 hertz. So this is my frequency, which gets like the frequency of the sound in the pipe. So now and now this frequency cannot change until I alter the sound source. After a time interval, a second much louder sound is heard. Calculate the time interval between the first louder sound and the second louder sound being heard. There has been no change in frequency, so there has been no change in wavelength. So wavelength is the same. And now there's a second much louder sound is heard, meaning that my piston has gone a bit behind. And what now happens is that there was another wave which just got formed. So like there is another stationary wave being formed, and this stationary wave would be of second harmonic frequency. So this stationary wave would be something like this. This is the second stationary wave which occurs. Like this wave with the second maximum amplitude wavelength and the second lowest frequency. Previously, in the previous case, this was my diagram was something like this. Just a second. Yeah, this is how my diagram was in the previous case. This is how it was. And now, when there was some, when the person got behind, so there was again an stationary wave formed, which was like this. The stationary wave formed was being formed like this. Now, so obviously, if I know how the wave was formed, I could simply calculate this distance. This is quarter wavelength, half wavelength. No, sorry, quarter wavelength, and obviously this would be half my wavelength, half my wavelength. So this whole thing would be equal to 1.25 lambda. Sorry, not 1.25. Apologies. 0.75 lambda. So this would be equal to 0.75 wavelength. So this is what this is equal to, 0.75 wavelength, and that's the new length. And from this, I could find the actual length of this whole thing, which I just did, 4.5 plus 4.5 plus 4.5. So this would give me 13.5 centimeters. This is my new length. So between the time that the first wave formed, the first stationary wave formed, and the second stationary wave formed, what's the distance moved by in pink, in blue by this piston? So I could simply say that initially the distance was just 4.5 and then it became 13.5. So this distance is 9 centimeters. Obviously, ignore the first drawing. It's not drawn to scale. So obviously, you can't say that this point is somewhere here. No, just ignore that part. But the distance is, but the key thing is that my piston has moved a distance of 9 centimeters behind. So the piston moved 9 centimeters between the time I heard the first stationary wave and the time between the time when I heard the second stationary wave. So it moved a distance of 9 centimeters. And what's the speed with which it's moving? It's moving at a speed of 0.75 centimeters. So it's moving at a speed of 0.75 centimeters, and it moves a distance of 9 centimeters. I could just simply divide this 9 divided by 0.75, and this will give me the time, which comes out at 12, which comes out as 12 seconds. So 12 seconds would be the time between when I heard the stationary wave of the maximum frequency and then the stationary wave of the minimum frequency. So 12 seconds would simply be my answer. So that's how you do this type of question, these type of questions. So like these were the questions that we're supposed to do, but there's just one more question which I'll just quickly gloss over. I'll tell you how it's supposed to be done, and maybe you could solve this yourself by taking a screenshot or whatever. So there would just be a difference. Like there is essentially no difference, I think. The piston right here was, there was an antinode on the open end where the loudspeaker was and a node where the piston was. This question is again something very similar to the previous one. And similarly, I know that there would be an antinode here, and for surely there would be a node at this point. So I know this, and this time, except it's just different that previously the piston was moving downwards, but this time the water is coming out from this nozzle, this tap. So the water is coming out, and they've given me stuff like how I could do this, or they've not given me the speed or stuff. Like it's just something similar to it. The same reasoning applies. So maybe you guys could do it yourself, because like just for practice, if you understood the concept correctly. So otherwise, and by the way, the question starts from part C. Whatever is before part C is not related. So if everything till now is straight to everyone, so then we'll end the class for today. So if anyone has any questions regarding what we've done right now, feel free to ask. Okay, and if no one has any questions, then we'll end the class today. And best of luck for your exam today. And like best of luck for the exam and for your future and whatever you do next. Okay, so assalamu alaikum.